Hi everyone. This work is about a new design approach named Action Transferred Design Approach of Navigation Techniques to support spatial learning in 3D virtual environments. This is a part of my PhD dissertation and has been published in ACM TOCHI journal in 2015. This work was mainly based on the university resources with no external funds. The original talk of this was already presented at the CHI conference in 2016. I made this talk a bit more comprehensive after the presentation at the CHI conference because I realized that a 15-minute talk was not enough for most people to understand this work unless they already read the original journal paper. For your information, this paper has 35 pages, excluding reference parts. So I hope this presentation helps you to understand the original work. To begin with, let me first a bit talk about some terminologies of interaction techniques, including navigation techniques. Interaction technique is a method consisting of all software and hardware elements to accomplish a task. Importantly, interaction techniques are defined using the user actions with some mathematical models. The task can be ranged from simple to complex. Usually, a complex task can be achieved by performing the combination of simple tasks. In VR, we call those simple tasks universal or fundamental tasks, such as object selection, object manipulation, navigation, and system control. This work was mainly focused on navigation because navigation is an indispensable task, even for the cases that navigation itself is not the main objective in the application. To accomplish the navigation task, users need navigation techniques that should be designed for the viewpoint control in virtual world. Since navigation is an indispensable task, you can see navigation in many VR applications. For example, dismounted soldiers can effectively engage the enemy's target or aerial targets via navigation in the training system. Navigation is also required to train firefighters so that they can successfully go through the search and rescue drill. VR systems can be more widely used for education and research by allowing the multiple users to navigate scientific data space and other data space together. Of course, navigation is more essential in VR games. Other application areas include architecture, building information management, virtual tour, and urban design. Then, how do people successfully navigate in VR? You may think about navigation aids. To answer this question, there are many navigation aids, landmarks, maps, and other haptic guides. Even you can use these navigation aids altogether. However, what if no navigation aids are available or feasible in certain tasks or applications? So fundamentally, it is more essential to acquire accurate spatial knowledge for successful navigation. Since accurate spatial knowledge acquisition is important for successful navigation, we first need to understand what spatial knowledge is. According to Seeger's work, there are three types of spatial knowledge: landmark, route, and survey knowledge. Landmark knowledge about recognizing visual landmarks and associating one's position with reference to the landmarks. Route or procedural knowledge is about understanding how to get from one location to the other. Survey knowledge is a mental representation of the environment, as knowledge is accumulated by experience in the environment. As implied by these definitions of spatial knowledge acquisition is a learning process. So spatial knowledge acquisition and spatial learning are interchangeably used in this work. Regarding the assessment, Roder suggested that different metrics are useful to assess different types of spatial knowledge. So we followed this suggestion when we came to assess spatial knowledge acquisition in our evaluation study. For example, landmark knowledge assessment is to measure how accurately the users represent and visualize the relative positions and arrangements of landmarks in the environment. Route knowledge assessment is to measure how accurately the users replicate the experienced route in the environment. Survey knowledge assessment is to measure how accurately the users represent the whole structure of the environment. So, what kind of navigation techniques can effectively support spatial knowledge acquisition in VR? According to the literature, many previous studies demonstrate that walking like navigation techniques supported better spatial learning than the others, such as one-device-based flying techniques. These kind of walking like navigation techniques include natural walking outdoor and indoor, treadmill-based walking in place, and one-device-based walking in place techniques. However, these walking like navigation techniques produced some practical usability issues, such as whole body fatigue, large physical space requirements, and high complex system configuration. These kind of practical usability issues make the walking like navigation techniques less popular and less widely used in various VR applications. Thus, we identified the research problem, which is there are inevitable trade-offs between convenience and effectiveness in navigation technique design. Again, walking like navigation techniques are more effective for spatial knowledge acquisition but less convenient. Non-walking like navigation techniques are more convenient but less effective for spatial knowledge acquisition. Let me here note that we provided the operational definition of convenience using the practical usability issues produced by walking like navigation techniques. So our research objective was to provide a design approach of navigation techniques to effectively support human spatial learning and also resolve the practical usability issues. Okay, how do we get the desired design? To answer this question, we need to see why the design trade-offs have not been resolved yet. So we looked closer at the previous studies and found a possible reason. Most previous approaches have been centered around walking like navigation techniques close to natural walking, maximizing the advantage of body-based sensory cues like proprioception and vestibular cues. As long as the design approach is stick to the walking like navigation techniques, the design trade-offs still remain the same. Instead, we took a little bit different research steps. We first focused on understanding human spatial learning because our ultimate goal is to improve human spatial learning, not to provide natural walking-based navigation techniques. We started by looking at the theories and obtained insights from the theories, and proposed a new design approach based on the insights. Instead, evaluating the design approach directly, we developed navigation techniques based on the design approach. Then evaluate the effectiveness of the navigation techniques for spatial knowledge acquisition. Thus, our design approach is not just borrowing the well-known metaphor, but combines theories and practice. As the first step of research method, let's see what we found from the theories. We first looked at the theories related to action and perception, such as ideomotor, common coding, and affordance theories. because virtual reality allows people to interactively act and perceive different sensory cues, such as visual, oral, and haptic cues. From these theories, we understood that action and perception are not independent but closely connected. Next, we looked at the theories related to learning, such as experiential learning and single-loop learning theories. These theories view the knowledge development as a cyclic process involving humans' motor capability. So, looking at these theories is really helpful to understand how to use humans' motor capability to support learning. This diagram shows the simplified learning model. The cyclic learning process suggests that plan plus act are referring to the goal-directed action. Review is referring to the perception. Based on this observation from the learning theories, we understood that goal-directed action and perception are not only closely related, but also core elements of learning. The most interesting observation is that none of these theories say that specific body parts are necessarily related to learning. So we don't have to stick to any specific body parts to improve the spatial learning. Then we saw another interesting theory named motor equivalence theory. This theory says that our brain recognizes the action as a motor pattern, not muscle or joint-specific motor commands. It means that as long as the motor pattern is equivalent, even though the motor pattern is executed by different body parts, our brain recognizes it as the same action. For example, we are able to write with our non-dominant hand or even with our foot without training after you learned how to write with the dominant hand. Our insight from this motor equivalent theory is that action can be transferred to the other body parts. Here is a summary of our theoretical findings about spatial learning. If a certain perception and action are known to support our spatial learning, then the same perception and the transferred action also support our spatial learning equally, as the theory suggests. So using this action transfer concept, we can develop navigation techniques to effectively support spatial learning and also resolve the practical usability issues. Here is our suggested action transfer design approach of navigation techniques. First, you choose an action effective for spatial learning. Based on literature review, we choose walking action. Secondly, you decompose the chosen action into sub-actions to find the simplified motor patterns. In our case, the sub-actions are gait cycle for moving forward, backward, and sideways, and body turn for changing orientation. Thirdly, you transfer the sub-actions to the different body parts with smaller muscle groups so then you can avoid any increased body fatigue. We chose fingers, and fingers are also known to support the final control. We call our action transfer navigation technique finger walking in place technique. Here, let me show how to design the finger walking in place technique. First, we transfer gait cycle sub-action to fingers for translational control of a viewpoint. This is very straightforward. You may think about walking on a treadmill. Then, we transfer the body turn to fingers for rotational control of a viewpoint. This is a little bit tricky because our wrist is hardly rotated 360 degrees. Instead, we use the pivot touch and drag technique. This action is similar to our body turn to change the orientation during walking. You know, we don't turn our bodies 360 degrees at once during walking. We implemented our finger walking place technique on many multi-touch devices, such as Limo MIDI device, iPhone, iPod Touch, and iPad. For our user study, we chose the iPad because it has largest touch surface. The finger walking in place technique can be straightforwardly implemented with the other devices, such as finger strap, ring, or gloves, or sensing technologies, as long as the devices are capable of detecting the finger movements of the finger walking place technique. As the last step of our research method, let me talk about our evaluation study. Our evaluation study was designed with the main hypothesis, which is the action transfer to navigation technique will achieve the better spatial learning effect compared with non-walking common navigation technique, but the same spatial learning effect as the walking like navigation technique. We designed a between subject comparative study using three navigation techniques: finger walking in place technique as an action transfer to navigation technique, joystick-based navigation technique as a non-walking common navigation technique, and sensor fusion walking in place technique as a walking like navigation technique. For convenience, I call these three navigation techniques FWIP, JS, SF-WIP, respectively, for the rest of this talk. Let me briefly show the JS technique and SF-WIP technique that we used for this study. We implemented the conventional wand joystick-based navigation technique as the non-walking common navigation technique. Basically, the user can control the viewpoint translation and rotation and movement speeds using the joystick, while the movement speeds were bounded by the buttons. For the walking leg navigation technique, we developed the sensor fusion walking place technique that is wire-free and supports dynamic walking speed, and even it supports running speed. As a VR system platform for the evaluation study, we used a 3-side wall and 1-flow cave system at Virginia Tech. We used 60 participants who completed all the experimental tasks. We assigned them to one of 3 navigation technique groups. We also made sure that each group is gender balanced, and all 3 groups are spatial ability balanced. We actually recruited more than 60 participants because there are some dropouts from each navigation technique group, mostly due to server sickness. I will visit this issue later. As a navigational virtual space, we made a virtual maze. We intentionally designed a virtual maze with a very limited visual information and made it a bit large and complicated to avoid any ceiling effect. This large scale and complex maze layout design was quite different from that used in previous studies. Since we used very limited visual information, we are only interested in route and survey knowledge acquisition. To assess route knowledge, we provided route learning tasks to all participants. For that, we designed three predefined routes. For each route, there is a learning phase. During this learning phase, each participant was allowed to learn the route through 3 times repetition with the waypoints and 2 landmarks. After the participant finished the route replication tasks, we removed all the waypoints, but all the 6 landmarks were visible to the participants for survey learning task. Each participant was allowed to spend up to 10 minutes to freely explore the maze until they were satisfied with learning the spatial layout of the maze. Now let's look at the assessment and data analysis of route knowledge acquisition. We first looked at the existing assessment methods. The task completion time and total distance traveled are generally used for route knowledge assessment. But our interest is not the faster performance of navigation techniques. Then the direction estimate to a target is also often used for survey knowledge assessment. Again, this method also provides only partial assessment of survey knowledge acquisition. Unfortunately, the assessment method typically used in the other studies were not applicable to our evaluation purpose, that is to measure the accuracies of acquired survey and route knowledge. For your information, here are two examples of how the participants perform the route replication tasks. The participant in the left-hand side missed many segments of the reference path. On the other side, the participant wandered some wrong segments but followed the reference path well. Can you find which participant performed better than the other in the route replication task using the existing assessment method? So we brought a new assessment method using penalty scores. First, we defined decision node and segments between two decision nodes on the maze. Then we calculated the penalty scores using the equation. If you look at the maze and predefine the routes, as I described before, you can find that there can be two possible mistakes that users can make during the route replication task, which are taking a wrong path and skipping the reference path. So we summed up all mistakes applied with reasonable probabilities which users made during the route replication task. Thus, the penalty was given to inaccurate route knowledge, but not the traveled distance or task completion time of the route replication task. These two graphs show the mean penalty scores of three navigation technique groups, when the weight value is 0.5 and 1 for missing segments. As you see the graphs, the mean penalty scores are much higher in the JS navigation technique group compared to other groups. Then we performed the statistical t-test to examine how this difference is statistically significant. As you see the table, the statistical results support our hypothesis that action transfers finger walking place technique supports route knowledge acquisition as good as SF-WIP, but better than JES in our maze environment. What about the time factor? Penalty scores might be affected by the task completion time as well as different navigation techniques, because different navigation techniques inevitably provide different navigation speed. You may wonder that FWIP showed better results than JS because the navigation speed of FWIP simply is much slower than JS. Is it true? We cannot answer to this reasonable doubt because time factor was not controlled in the t-test. So we performed another statistical test, analysis of covariance, controlling the time factor. And we got the result here. As you see the statistical result in the table, the ANCOVA test results are consistent with the result of t-test, but much strongly support our hypothesis after removing the effect of time covariate on penalty scores. It means that if all navigation techniques provide the same speed, then the FWIP navigation technique would show much better effect on spatial learning compared to the JES navigation technique. Let's look at the assessment and data analysis for survey knowledge. To assess survey knowledge acquisition, we provided this maze map-based multiple choice question to the participants after they completed the maze learning tasks. Among these 6 choices, all participants chose one single maze as they thought it was correct. The table shows the responses of the participants in the 3 navigation technique groups. Out of 20 participants in each navigation technique group, the JES group showed 30% correctness, and the FWIP group showed 60% correctness, and the SF-WIP group showed 45% correctness. In order to analyze this data, we were advised by the statistical consulting group at Virginia Tech, and we conducted a chi-square goodness of fit test to examine whether each group participants acquired the survey knowledge of the maze environment. The hypothesis of the chi-square goodness of fit test for our data is that if the probability of the population with the correct answer in the navigation technique group is statistically greater than 1/6, then we can conclude that the users in the navigation technique group acquired survey knowledge after the maze experience. Here is the result of the chi-square goodness of fit test. As you see the table, this test found the statistically significant difference of the number of the correct answers chosen in the FWIP and SF-WIP navigation technique groups, but not in the JES navigation technique group, compared to the probability, which is 1/6 of a randomly chosen correct answer. It means that participants in the FWIP and SF-WIP, but not in the JES group, acquired survey knowledge of the maze. Here is a summary of our evaluation study results that FWIP technique is better than JES technique for spatial knowledge acquisition, and FWIP and SF-WIP navigation techniques showed a similar effect on spatial knowledge acquisition. Thus, we confirmed that these study results support our hypothesis. So far, I presented how we can develop convenient and effective navigation techniques to support spatial knowledge acquisition by resolving the issues of walking like navigation techniques. Before closing this talk, I would like to visit the cyber sickness issue again that we observed during our study. If you see the dropout rate, you can notice that dropout rate is much higher in the JS group, while the other groups show the relatively lower rate of dropouts. So regarding cyber sickness, we attempted to understand cyber sickness with the relationship between navigation techniques, walking action, and full body movement. And it looks like cyber sickness mitigation is more related to walking action, but not full body movement. This conjecture may be a little bit exaggerated because we have only a small single case. However, it is worth further study because our study certainly showed that there is a correlation between walking action and cyber sickness mitigation. Based on our observation regarding cyber sickness, we have a potential research question. We first surveyed some relevant theories, but we found that a fully adequate theory of motion sickness is not presently available. Instead, there is a well-known theory named sensory conflict theory. This theory says that the motion sickness occurs when the brain receives conflicting sensory information from our body, inner ears, and eyes. Regarding service sickness, our potential research question is, what if the conflict is about the action and perception, but not about sequential muscle or joint-specific motor commands and sensory information? If so, based on our theoretical findings and the literature review, we might mitigate service sickness by doing one of the followings. As we observed in our evaluation study, using the action transfer the interaction technique can reduce the service sickness, in particular when the tasks cause heavy cognitive load. As the common coding theory suggests, watching the action and doing the same action result in the same code in our brain. Instead of controlling the user's viewpoint directly, if the user controls and watches the avatar that is performing the walking action, then the conflict might mitigate the service sickness. However, in this case, another conflict can occur between controlling the avatar and watching the avatar's walking action. The last one is to use natural walking like navigation techniques, as many previous studies demonstrated. However, you remember that these walking like navigation techniques produce practical usability issues, so that the design trade-offs still remain the same. Here is the conclusion of our work. As theoretically and empirically demonstrated in this work, our action transfer design approach effectively and conveniently supported human spatial learning. Let me finish this presentation by listing up some potential applications of action transfer design approach. We think this action transfer interaction technique design approach can find many real applications. First, the FWIP technique can be immediately applicable to the field of training and learning, in which effective spatial learning is essential but physical training is unnecessary. Examples include military training for understanding enemy's bases, virtual exploration of scientific data sets, and virtual tours in museums, art galleries, and history places in the world. The FWIP navigation technique can even be useful for the public without dedicated VR systems, which can extend the FWIP technique's benefits to other types of VR applications, such as virtual tours, architecture or urban design, virtual adventure games, and gamified learning, exploration of virtual communities like a Second Life, and operation of unmanned vehicles. If the action transfer concept is applied to the other interaction technique design, then it can be useful to design customized interaction techniques for people with functional disability of body parts. Designing customized interaction techniques is also useful when a replacement is desired due to fatigue or convenience reason. The action transfer concept may be utilized to design interaction techniques for interactive mobile VR, reducing service sickness. For this purpose, further study is strongly suggested. In addition, the current mobile VR is mainly based on head-mounted set, providing a fully immersive virtual environment. This fully immersive virtual environment makes users completely block out the outside world. So with this fully immersive VR, users can be very risky if they physically walk around. They may have some equal benefits without physical movement if they use action transfer navigation techniques. Thank you for your attention, and please find our TOCHI paper for more details.